In this video, we're going to discuss how to find the area between curves, which is an application of integration. And here we're going to find the areas with or without the help of the graphs of the functions. Let's get started. Suppose we want to find the area of this region, which is bounded by two functions, bounded above by f and bounded below by g, and from x equals a to x equals b. So the region is also bounded by this vertical line x equals a and x equals b. How do we find the area of this blue region? That is very easy with the help of calculus, because the area of this region is just equal to this definite integral from a to b of the difference of the higher function, which is f of x, minus the lower function, which is equal to g of x. Take note that when we use this formula to find the area bounded by the two functions, we assume that these two functions here are continuous on the closed interval ab, and f of x is greater than or equal to g of x. This formula follows from the geometric interpretation of definite integral. If we look at some cases, if we look at this first case here, where we have this as our function f, then we know already how to find the area of this region, because this is just the region under the curve f on the closed interval AB. And we know that that is just the integral from a to b of f of x dx. But we can also consider this region as a region bounded by two curves. And what is the other curve in this case? The other curve is actually the x-axis. So this is our function g in this case, which is also a function of x. And its equation is, of course, g of x equal to 0. So when we plug in g of x equals 0 into our formula, we'll get here integral from a to b of f of x minus 0 is just f of x dx, which is equal to this one. And we know that if we have a non-negative function, the value of this definite integral is just the area under the curve. In this case, it is equal to a. Let's look at another case. If we consider this region here, which is bounded below by a function g, then how do we find the integral from a to b, of g of x dx? It is equal to, since we have a region below the x-axis, then this is just equal to negative a, where a is the area of this region. Now, using this formula here, this region is also bounded by two functions, and again, it is bounded above by a function f. And what is our function f? It is the x-axis again, which has an equation f of x equal to 0. Using this equation again, we can find the area of this region by plugging in f of x equals 0, and we'll get here integral from a to b of 0 minus g of x dx, which is equal to negative integral of g of x dx from a to b. And as you can see, we'll get also here negative a, which is equal to integral from a to b of g of x dx, which is consistent with the geometric interpretation of the definite integral. Let's consider another case. So if we look at the case where both f and g are positive, the formula is clear from this figure. So we have here the area of this region is just equal to the area of the region under f, which is the definite integral of f of x dx from a to b, minus this green region here, which has an area equal to the definite integral of g of x dx from a to b. So it follows that the area of this region bounded by the two functions f and g on the closed interval ab is equal to this integral here minus this integral, which can be written as integral from a to b of the difference dx. So we can use this formula here for any f of x and g of x as long as f of x is greater than or equal to g of x on the closed interval ab. And take note of the assumption that f and g must be continuous on the closed interval ab. So from this, it is very easy to find the area between two curves on a closed interval AB if we know which function is higher than the other on the closed interval AB. The question now is it possible to find the area between two curves on a closed interval AB without sketching the graphs of the functions? The answer is yes. To find the area of the region between these two curves, y equals f of x and y equals g of x over the interval AB, where f and g are of course assumed to be continuous on the closed interval AB, we just have to compute for the definite integral from a to b of the absolute value of f of x minus g of x dx. So in this case, we have here absolute values instead of just a grouping symbol. Now, how do we evaluate this definite integral with absolute value in the integrand? So the strategy here is to split this into sum of integrals. And how do we find the limits of integrations of that integrals? All we need to do is find the x values that will make this f of x minus g of x equal to 0, which means that we're looking for the x coordinates of the points of intersection of the graphs of f and g. So for example, at this point, f of x is equal to g of x, so therefore f of x minus g of x is equal to 0. Also, at this point of intersection, we have f of x minus g of x equal to 0. And here at the left endpoint, we also have f of x minus g of x equal to 0. Now, we use these x coordinates here to divide the closed interval AB. So in this case, we can divide, let's say, this integral from a to b as integral from a to c plus integral from c to d and then plus integral from d to b, only using additive property of definite integral. Now, for each of these closed intervals here, we know that f of x minus g of x is either greater than or equal to 0 or less than or equal to 0. So therefore, we can already remove the absolute value in these integrands. For example, if we look at this closed interval a to c, so f here, this is our function f, is greater than or equal to g. So therefore, f of x minus g of x is greater than or equal to 0. So the absolute value of this expression, which I represented by this asterisk, is just equal to itself because the value is greater than or equal to 0 on the closed interval AC. But if we now consider this closed interval CD, then g is higher than f. So f of x minus g of x is less than or equal to 0. And the absolute value of a number that is less than or equal to 0 is the negative of itself. So it's the negative of this difference, f of x minus g of x. And lastly, if we look at this integral here, so we're integrating from d to b. Again, f is higher than g, so f of x minus g of x is greater than or equal to 0. So again, we can replace this absolute value by just f of x minus g of x. Now, what if we're not given the following graphs? So how do we remove the absolute values in the integrands? After dividing this definite integral into these three integrals, where c and d are the only zeros of f of x minus g of x between a and b, we are sure already that the value of this expression here, which is equal to f of x minus g of x, is either greater than or equal to 0 or less than or equal to 0. So to determine whether the expression inside is greater than or equal to 0 or less than or equal to 0, all we need to do is what? Plug in a test value, a number which is between a and c. So if a is equal to 0 and c is equal to 4, then you may choose x which is equal to 1 and plug in 1 in this expression and check whether it's positive or negative. If it is negative, then we are sure that this expression is less than or equal to 0 throughout the closed interval AC. And we'll do the exact same thing for this integral and for this integral. So if we know that this expression is less than or equal to 0 on the closed interval AC, then absolute value of that expression is the negative of that expression. But if this is greater than or equal to 0, then we can just get rid of the absolute value bars. Let's have some examples. Suppose we want to find the area of the region enclosed by the curves f of x equal to 5x plus 1 and g of x equal to x squared plus 3x minus 2. We know already the graphs of these two functions. So the graph of f is just a straight line with positive slope. So it's an increasing line. And the graph of g, it's a parabola that opens up because the coefficient of x squared is 1, which is positive. So we would expect that the graph looks something like this, and we are interested in finding the area of this region enclosed by the two curves. So it is already clear that the line is higher than the parabola in this case. But to find this area, we need to determine the x coordinates of the points of intersection, which will become the limits of integration of our definite integral. So let's find those x-intercepts of the points of intersection. So to find them, again, points of intersection, so we have the same function values, f of x equal to g of x. So we have here 5x plus 1 equal to this trinomial, and then move all the terms to the right-hand side. You'll get here x squared plus 3x minus 5x, so that will be minus 2x, and then minus 2 minus 1, so that is minus 3. And we can factor this to x plus 1 times x minus 3. Therefore, the x coordinates of our points of intersections are x equals negative 1 and x equals 3. So we can now find the area of the enclosed region, and it is just equal to integral from negative 1 to 3, which are the x coordinates of our points of intersection. And then what will be our integrand? It will be the higher function, which is the line f of x equal to 5x plus 1. And then minus the lower function, which is this parabola here. So we have x squared plus 3x minus 2. So don't forget the grouping symbol here because this is a subtraction. So the grouping symbol is very important. Now we simplify first before we find the antiderivative of the integrand. So this one here minus x squared, and then 5x minus 3x, so that is plus 2x, and then 1 minus minus 2, so that is 1 plus 2, which is equal to 3. And now we find an antiderivative of this expression. We'll get negative x cubed over 3 plus 2x squared over 2, which is x squared, and then plus 3x, evaluated from negative 1 to 3. And now we plug in the upper limit first. So plug in a 3 into this expression. We'll get here negative 9 plus 9, and then plus 9, minus plug in the negative 1 into this expression, which gives positive 1/3 plus 1, and then minus a 3. And this is just equal to 9 minus, this is 1/3 minus 2, and 2 is just 6 over 3. So this is equal to negative 5/3. So 9 minus negative 5/3. So 9 is just equal to 27 over 3 plus 5 over 3. So we'll get here 32 over 3 square units. And this is the area of this region enclosed by the line and the parabola. Now, how do we solve this problem here without sketching graphs of these two functions, f of x and g of x? We can do that by first finding the x-coordinates of the points of intersection. We found them a while ago already, and they are x equals -1 and x equals 3. This implies that the area enclosed by the two curves is equal to this definite integral here from -1 to 3, because -1 and -3 are the x-coordinates of the points of intersection. And then we have here absolute value of f of x minus g of x dx. Now, in case that the two curves have more than 2 points of intersection, then in that case, we have to use the smallest x coordinate here and then the largest y coordinate here. Let's say the x coordinates of the points of intersection are -3, -1, and +5. Then for this case, the area bounded by the two curves will be use the smallest x coordinate as the lower limit of integration. So you have there -3, and use as the upper limit of integration the largest x coordinate, which is in this case, it's equal to 5. But since we only have here 2 points of intersection, so we just use the lower value as our lower limit and then the higher value as our upper limit. Now, the order of f and g here is not important because we have this absolute value. So you can write this f of x minus g of x as g of x minus f of x. So what is our f of x? It is equal to 5x plus 1 and then minus this g of x here. And when we simplify this one, we'll get -x² plus 2x plus 3. Now, to evaluate this integral, we have to remove the absolute values. But we need to determine whether this expression here is greater than or equal to 0 or less than or equal to 0 on this closed interval -1 to 3. So as I said a while ago, we just have to plug in some value between -1 and 3. So let's say plug in 0, you'll get here 0 plus 0 plus a 3. It's positive. So we are sure that on this closed interval, this is greater than or equal to 0. And since it is greater than or equal to 0, its absolute value is just equal to itself. And we have evaluated this integral already a while ago. And we got 32 over 3 square units. Let's have one more problem. Let's find the area of the region or regions between the curves f of x equal to 5x plus 1 and g of x equal to x² plus 3x minus 2 over the closed interval -3 to 4. So suppose we don't know the graphs of f and g, and we want to find the area of the region or regions between these two curves over the closed interval -3 to 4. So how do we find the area? It is only equal to the definite integral of this absolute value of f of x minus g of x dx on this closed interval. So the limits of integrations will be -3 and +4. Now, how do we evaluate this integral? We have to find the x coordinates of the zeros of this f of x minus g of x And we're going to use those x coordinates to divide this closed interval -3 to 4. But we found already the x coordinates of the zeros of this f of x minus g of x. So these are just the x coordinates of the points of intersection, which are -1 and +3. Therefore, this integral here, which can be written as this definite integral, and simplifying this expression here, we'll get this expression. This integral can be divided into three integrals. Again, we have to use this -1 and 3 to divide this interval -3 to 4. So we'll get here three intervals. We have from -3 to -1, -1 to -3, and then a 3 to 4. Now, we will be able to remove already these absolute values here because we are sure that the expression inside is either greater than or equal to 0 or less than or equal to 0. So for example here, you can choose x equals -2 here, and you plug in x equals -2, you'll get here -4 and then -4 plus a 3, which is a negative number. So therefore, this is less than or equal to 0 in the closed interval -3 to -1. Since it is less than or equal to 0, its absolute value is the negative of itself. Now for this interval here, so we can plug in x equals 0, and if you plug in x equals 0, this is greater than 0. So therefore, it is greater than or equal to 0 on the closed interval -1 to 3. And it follows that its absolute value is equal to itself. And here you can plug in a 3.5 if you want. And you'll see that the value of this is negative. So this is less than or equal to 0 on the closed interval 3 to 4. So the absolute value is the negative of the expression. Another way to determine the sign of this expression here is to draw a sign chart for -x² plus 2x plus 3. And you'll see that the sign chart for that one, so the x values that will make it 0 are -1 and +3. And you'll see that the sign of that one will be negative, positive, and negative. And one way also to determine its sign is if you think of the parabola y equal to this expression, then the graph is just a parabola that opens down where the points of intersection is at -1 and at a 3. It's a parabola that opens down. So therefore, its value is negative when x is greater than 3 and when x is less than -1. And it is positive between -1 and +3. So those are three ways on how to determine the sign of the expression inside the absolute value bars. Now we can easily evaluate these three integrals here. So an antiderivative of this expression here, which is exactly the same thing as this one, is x cubed over 3 minus x squared minus a 3x. And since this is just negative of this expression, of this integrand, then an antiderivative is the negative of this one, which is equal to this expression. Now what's left is algebra, so we just plug in -1 first into this expression, and we'll get -1/3 minus 1 plus a 3, and then minus, plug in the -3 for x in this expression, and we'll get here -9 minus 9 plus 9. And then plus, we found this one a while ago already in the previous problem, and its value is equal to 32 over 3. And now we plug in this 4 into this expression, we'll get this one, and then plug in 3 into this expression, we'll get 9 minus 9 minus 9. And this expression here is equal to 32 over 3, and then plus 32 over 3, and then plus this expression is equal to 7 over 3. So the area is equal to 71 over 3. If we go back to the graphs of these two functions again, okay, so f is just an increasing line and g is just a parabola that opens up. So in this case, we were looking for the area of the region or regions between the two curves. And here we have three regions between the two curves on the closed interval -3 to +4. So this is our -3, and then this is our +4. So we have here three regions, this one, and then this one, and then this one. And we see that in this first region, the parabola is higher than the line. So actually this expression here is the same thing as g of x minus f of x. And then on the closed interval -1 to 3, the line is higher than the parabola. So in this case, this expression is equal to the line, which is f of x, and then minus g of x. And then in this third region here, the parabola is higher than the line. So this expression here is equal to g of x minus f of x. So if you know how to sketch graphs of functions, then you can easily set up your integrand in this case because you'll know which function is higher than the other on a given interval.